Okay, today we're going to do section 1-2 for Algebra 2, and it's on the properties of real numbers. Okay, properties of real numbers. First, there are several sets of numbers that we have to define. The first is the set of real numbers. When you talk about real numbers, those are all the numbers on the number line. All the numbers on the number line. And I will always use, most books use a italic R. I use a double bar R, and that will represent real numbers. Okay, the next set of numbers that we need to talk about is the set of rational numbers. Rational numbers, that's every rational number is a number that can be written, a number that can be written in the form and they might use different letters. I'm using M over N, where M and N are elements of, that's the Greek letter epsilon. Epsilon is read is an element of. M and N are elements of the set of integers. They use the brace. It stands for the set of integers. Okay, and we'll get to integers in a minute, but basically it's examples like 1 over 6. 1 and 6 are both integers. 2 over 3. 2 and 3 are both integers. Negative 1/2. Negative 3/4. Those are all rational numbers. If I said the number 5, 5 is a rational number because I can write it as 1 over 5. Okay, so those are all examples of rational numbers. Also, you need to know about the decimal form. Okay, a rational number can be written, a rational number can be written as a repeating or terminating. A rational number can be written as a repeating or terminating decimal. For example, 1/2, I can write that as 0.5. 1/3, I can write that as 0.33333 repeating. You can show it with the 3 dots, or you could show 0.3 with a bar above it. That means it's repeating. If I had, let's say, 0.12, and I want both of them to repeat, so that's 0.12, 12, 12, and it's repeating. So a rational number, if it's a repeating decimal or a decimal that stops, okay, like if I said 0.89, that would be a rational number. Okay. The next set that we need to talk about is the set of irrational numbers. And these are numbers that cannot be written in the form M over N, where M and N are elements of, or M and M are elements of the set of integers. So no matter how hard you try, you cannot write an irrational number in that form. Okay, so example, probably the most famous irrational number is pi. Now, pi is approximately 3.14, but it does not terminate, it does not repeat. Sometimes we write it as 22/7, but that's a rounded value. Okay, so pi is an irrational number. Examples like square root of 2, square root of 3, square root of 5, square root of 7. No matter how hard you try, you cannot put those in the form of a fraction where the two numerator and denominator come from the set of integers. Okay, and decimal wise, an irrational number is a non-terminating, that means it does not end, it does not terminate, a non-terminating, non-repeating decimal. So like if I did 0.01, 001, 0001, 00001, and so on, it does not repeat one specific pattern. It does not have the same amount of zeros in between, and it does not terminate. You have to have the ... to show that it does not terminate. Like another example would be if I had 1.232233 22233, and then ... So those are examples of irrational decimals, irrational numbers. Okay, so we've done real numbers, all the numbers on the number line, rational numbers in the form m over n, where m and n are integers. Irrationals, you cannot put them in that form. Okay, the next set of numbers we need to talk about, and we actually mentioned them up above because we've worked with them in Algebra 1, the set of integers. The set of integers, and it is a set, so you need the braces, and it starts 0, positive 1, positive 2, positive 3, ... and then in the other direction, negative 1, negative 2, negative 3, ... in this direction. Okay, notice like the fraction 1/2, the fraction negative 3/4, those are not integers. Okay. Then the next set is the set of whole numbers. Whole numbers are 0, 1, 2, 3, 4, and so on, ... And then natural numbers. Natural numbers are usually where we start. They sometimes call them natural numbers or counting numbers. Counting numbers start with the number 1, 2, 3, 4, 5, ... They just keep going. Notice 0 is a whole number. 0 is not a natural number or counting number. Okay. Okay, and there's a couple ways to visualize this. Draw a pretty good sized box on your paper, like so. One way is to do like a graphic organizer, and this box would represent all the real numbers. That's all the numbers on the number line. Okay. Split the real numbers. On this side, let's put the rationals. And they will use the letter Q. For the reals, we're going to use a double bar R. And then on this side, let's do the irrationals. So the real numbers are made up of rationals and irrationals. The irrationals are going to use an uppercase I. Okay, within the rationals, let's put a circle. Okay, and you have the set of integers. In the integers, they're going to use an uppercase Z. to represent the integers. Inside the integers, we have the whole numbers. And the whole numbers are going to use an uppercase W. And inside the whole numbers, we're going to have the natural numbers. We're going to use an uppercase N. So, the natural numbers start 1, 2, 3. They would be in here. Okay, and then if you put 0 in there, then your 0 is a whole number. It is not a natural number, but 0 would also be an integer. It would also be rational. It would also be real. Anything that's irrational would also be real. Okay. Another way to do this is to do a different kind of organizer. Okay, and let's draw that from the bottom of the page. Let's go all the way to the bottom and draw. Let's start with the natural numbers, and that's usually where we learn to count. Little babies learn to count with natural numbers first. Okay, the natural numbers, and we usually start with number 1, 2, 3, ... And they are set, so use your braces. Okay, and then if we put 0 in there, 0, then that ends up making up the whole numbers. 0 is a whole number. It is not a natural number. Whole numbers, that's the set 0, 1, 2, 3, ... Okay, if you take the whole numbers and put in the negative integers, okay, and the negative integers would go this way: -1, -2, -3, ... to the left. And then the negative integers and the whole numbers together make up the set of integers. Notice how you spell that. It's I-N-T-E-G. It's not integers, it's integers. Okay, and the integers are 0, 1, 2, 3, ... and then -1, -2, -3, ... So the integers are made up of whole numbers and negative integers. Okay, and then if you take the integers and include the fractions, like 1/2, 3/4, okay, then you end up with the rationals. And remember, with the rationals, okay, they are going to use Q for the rationals, I for the integers. Okay, then the rationals, and then if you take the rationals and the irrationals, and those will make up the reals. And let's use a double bar R for the real numbers. And that's as high as you've gone so far, the real number system. So remember, they're going to use I for the irrationals, Q for the rationals, double bar R for the reals. For the integers, they're using the letter Z. Okay. For the whole numbers, they'll use a W. Okay. Okay, so that's another graphic organizer. So if you say, okay, what about the number -5? Okay, -5 would be a negative integer, which makes it an integer, which makes it rational, which makes it real. If you said, what about the number 7? 7 is a natural number, means it's a whole number, means it's an integer, it's rational, it's real. It would be in all those sets. Okay. So you can use either graphic organizer to help you on the problems. Okay. Okay, then the author goes through some properties that we need to go back and review. You've had these in Algebra 1, so it shouldn't be much of a review. Up at the top, put for all, and I'm going to use a double bar R for all real numbers, A, B, and C. Okay, and let's make a table. I need the 3 columns basically. Okay, and let's review the commutative. It's not commune, it's commutative property. And for, let's make this column be addition and this column be multiplication. Okay, and the commutative property says A plus B equals B plus A. So 2 plus 3 equals 3 plus 2. And then for multiplication, A times B equals B times A. Okay. They commute or they change places around a plus sign or a times sign. The next one is the associative property. Okay, and for that one, they are in the same order, A plus B plus C. They have to be in the same order, A plus B plus C. And it's just a regrouping. So if we group these two together, A plus B, group these two together, B plus C. And this one would be A times B times C. They have to be in the same order, A times B times C. And all you do is regroup. Okay, and that's the associative property. You have to use these properties when you're solving equations. The identities. Okay, for addition, additive identity, A plus 0 equals A. For multiplication, A times 1 equals A. So 0 is the additive identity, 1 is the multiplicative identity. Then the author also talks about inverses. The additive inverses is A plus the opposite of A, brings you back to the identity 0, and A times 1 over A equals 1, and the A cannot be 0 because you can't have division by 0. So that's the inverse. Additive inverse, multiplicative inverses are also called reciprocals. Then the author also talks about closure. The closure property says that if you take two real numbers, A plus B, you're going to get a real number back in the set. Closure means you get a number back in the set. And if you multiply two real numbers, you get a real number. Means you get a number back in that set. And then the distributive property, most of you have used this a bunch. A times the quantity B plus C equals, and usually I draw the arrows, A times B plus A times C. Okay. Okay, now let's look at if they give you a number and they want to know all the types of the sets that it belongs in. So name the sets of numbers to which each number belongs. Okay, let's say they give you the square root of 6. So you go back and you look at that chart and say, okay, where does it begin? You can look at this chart or the other one. Square root of 6 would actually fit up here in the irrationals. You cannot get it in the form of P over Q. So if it's an irrational, then it's also a real. Okay, so it's irrational, which would be I, and it's also real. 5 would fit into the natural numbers. Okay, and you can work your way up. If it's a natural number, it's also a whole number, it's also an integer, it's also a rational, it's also a real. Negative 2/3. That one you can put it in the form of a fraction, m over n. where m and n are integers, so that is a rational number, and if it's rational, it's also real. Negative 43. Negative 43 would fit in, first place it would fit in would be the integers. And then if it's an integer, it's rational, it's also real. Okay, and the last one, negative 23.3, it's a decimal that terminates or stops, so it's rational, and that means it's also real. Okay? Okay, that should be enough to get you started on the assignment.